The level is also the same, that 58845, the same thing. I just did it manually, the same also. So, yeah. So you have to release the water, at least 20% of the water must be released. Actually, this bottom outlets also used to flush the sediment in the future. But I was surveying dam site in Eritrea. Curve. This is the graph of the storage and elevation curve. So these are the things we need to run the model. And the other important thing here. Hello, this is Masfin. Today I came up with the hydrologic design of a dam. Using software tool, HEC-HMS. I did the same hydrologic design to the same dam, the Grand Ethiopian Renaissance Dam, and I used manual calculation. So now I am verifying it using with the Logicel. As a procedure is simple, using. So just simply to summarize the previous hydrologic dam design, this was the PowerPoint that I explained. This is the salient points of the dam, and this is the location, and this is the catchment area. Catchment area in 3D. This is the dam, and this is the western Ethiopia. This is actually the dam, and this is the same. And this is how I calculated the volume of the dam using ArcGIS. I showed some, and this is the previous old method of calculating. This is now digital, and this was me while I was surveying dam site in Eritrea. And this is the GIS system to calculate the volume of water. You can see the previous video. And this is the dam, and this is the result I found from the GIS. Volume. This is the maximum volume face area. And this is actually the elevation. You see, this is 4 diversion bottom outlets. There are 4 bottom outlets to release the water directly without, block. You can't block the water completely. I mean, while constructing even. So you have to release the water. At least 20% of the water must be released. Actually, this bottom outlets also used to flush the sediment in the future, but now you have to you can use it just simply to release 20% of water to the downstream user. This is the elevation that you can see, the minimum elevation. 542 is the water must be reached to this level to be released into. Actually, the penstock is at 560. Okay, 14 of them. These are 2 of them. Therefore, the water needs to be reached to this level to be released to the penstock. Actually, not only to this level, there should be some head. There should be some head. So you can't, I mean, there is no head. You can't generate any electricity here. You need to have some head so that the water will have a pounding effect. It can run and hit the turbine, you know. So there should be some height above, but the outlet level, of the penstocks above of 560 and 542. That's the minimum operating level, exactly 590 meter. Almost how much? 30 meter for the 14th. We need to have 30 meter for the 14th, and the others needs to be 50 to something like that, 50.25 meters, 30 for the 14 turbines, and 52 for. Then this is a spillway level. You know, the ogive free spillway is this. This is the spillway at the other side of the dam. You see, the spillway. Let me show you. This is a spillway here. Spillway. There is a spillway. This is a dam. The dam has at the top. There is a one spillway, 640 meters. And at 624.9 meters, there is another spillway. If it's needed to release, I mean, if it is necessary to release the water, then this can be opened and be released. But normally, it's just closed. You see, when there is flooding, inundation, or if the incoming flood is much higher than the capacity of the volume, I mean the capacity of the reservoir to hold the water, then the spillway, the gated spillway can be opened up and the incoming extra water can be released in case it is necessary. So the spillway is necessary. And on the top of the dam there is another spillway as well. So there is the spillway here. This is the top of the dam. You can see these are the two penstocks turbine. This is the penstock. It's just a part. I think 8 meter, 4 meter. Let's see. So that is it. Storage capacity curve. Billion meter cube. Area division curve. These are manually calculated. Elevation versus discharge capacity curve. This is the scenario here. The scenario is we assume those four gates at the bottom of the dam are closed. That is the assumption to calculate the volume. You see, we can open them and calculate the water that can be released, but instead, I chose to close them. That's all. It's not a matter of, I mean, difficulty or anything else. We can add them. We can calculate the effect if we open the dam, open the sluice gate, the four lower gates possible. But in this case, I assume they are closed. And let us assume that they are closed and only the turbines are functioning. I mean, if I was there and know the exact situation, I can change all these steps and recalculate it, but this is what I assume too. The main thing here is calculation steps to arrive into the right estimation. We can say it's an estimation hydrology. So that is it. These are the calculated values of the storage indication curve. And this is storage indication curve. This is the data obtained from. This is the guys who I know the guy. I know some Askedo, I don't know, but this guy, And this is the water. I mean the inflow hydrograph I use. That's the mean of 5 years, 2040 up to 2090. It's just hydrology. So these are the data observed. This is data observed data. See, you can see the peak inflow is this one. It is in août. Août means August. This is in français, janvier, février, mars, avril, mai, juin, juillet, août, October, November, and December. We use English and French. That is it. And this is the calculation I made manually. And the elevation level is this one, the outflow. This one is a bit higher than the one which is calculated in the HEC-HMS, because the reference, the interpolation I use is, this one. I use this one. This one and this one calculates the outflow. But the HEC-HMS calculates using the elevation versus this one cumulative, or this one, the elevation versus the outflow, I think. And it calculates a bit different. But I did also the same. That's all. So now we can see the manual calculation, how I did it. So and then we will see the HEC-HMS. Yes, that is the Excel. That is the yes, the elevation storage curve. So calculation is done here, and this is assumption scenarios. This is a weir level flow. The weir discharge is this one. When it reaches 641, every outlets can be used. It's a monthly flow and the observed flow, and this is the calculation. Then this is the outflow calculation, interpolating, from here, interpolating from here. So the elevation, the HEC. I did the calculation using this interpolation, using the elevation. And this one, yes, I found out exactly the same with the HEC-HMS. So that's it. Previously I did interpolate this one with this one against this one, but it should be this one against this one, I think. So that is a little bit error. That is 54 billion meter cube, Now it is 51 billion, according to the HEC-HMS. So probably that one is very simple mistakes, errors, I think. And these are 0, 0. This is an assumption because everything is closed between January and June. The water can't be released because the 4 diversion or sluice gates are closed, so no water going out. That's an assumption. That's a scenario. It's not a real case. So we have closed there, but we can simply calculate that 20% of inflow can be released. It's inflow directly. 20% of it can be calculated, but not necessary actually. And this is manually. I have calculated the volume of water and so on. Anyway, that is it. But now let us see the HEC-HMS. Yes, it's coming. So here is the HEC-HMS. Yes, you can see here. This is the way how to read the inflow reservoir. They have to be connected. I did this thing before, so you can see that. So this is how I did it. There's a control. This is time series. I use a hydrograph, 1 day step, time step. This is the graph, and the other pair data. This is the duration curve. This is the graph of the storage and delineation curve. So these are the things we need to run the model. And the other important thing here is that still we need to calculate manually the storage, the discharge curve, the deviation curve. Everything we did necessary even to use here, to bring them here. It is important to have all those manually calculated values so that we can calculate so we can run the model. So now we can see here the results. Maybe let's see the result. Yeah, just simply to show I can run the result again. This is the result. You can see that it is okay. Yes, 100%. Then that is it. This is the value, 52 billion times 1,000 billion meter cube of water can be stored in 1 year. Much of the water comes in the season, the rainy season, Then the outflow, based on our scenario, if we are going to release everything that comes through the penstock, running through the turbine, and then 42, 43 billion meter cube of water can be released out. As long as the turbine is running, every water that is coming will go out, But to accumulate extra water and so on, it needs time. We have to close it for some time and so on, so that we need to accumulate. The turbine needs to work continuously. You can't run it once and finish the water and stop it. It's not like that. It can't be. Otherwise it causes damage, if the electricity stops, factories are going to stop. It's very difficult. So it needs to be smooth. Always there should be some quantity of water flowing constant throughout the year. So it needs to be stored and needs to be studied so that how much water must be released throughout the year continuously without affecting the downstream side, without affecting the electric generation. The generation of electricity has to be same all the time. You can't say, no, we are sorry, we don't have electricity today. If it is in Europe, the company will ask, or company, any factory, who lost the profits or because of the interruption, electricity interruption, the government or the one who is controlling the dam, any institute has to reimburse the money to the company. The inflow hydrograph, the summary, you can see that is the volume of water. Nash Stuttgart as one. That is it at peak. Everything, the advantage of having the software is everything will be detailed. You'll have every information. You see, and the level is also the same. That 588, 45, the same thing. I just did it manually, the same also. So, having the software means it doesn't mean that you don't need to have the knowledge. Or anyone who just simply can run the model, maybe it's very difficult for him to calculate, as long as, if he's not a hydrologist, have no idea about or maybe little knowledge, then it's very difficult to run the model. Still, you need to know to run it manually and be able to interpret everything, as a hydrologist. So that is so. One has to have the knowledge of both. This is a tool. It can't be a replacement it can't replace a hydrologist, I can say. So that is it. So every detail, the red one is the storage. You can see almost 14 billion meter cube of water accumulates just at the time of the peak. That is it. In total, it's obvious, after the peak also, there are some water coming, so that is it. So you can see. Maybe this one is, this is combined inflow. Combined inflow is maybe it's as groundwater. So that is it. That is it, summary table. This is reservoir, the discharge, the volume that is discharged, the volume that is stored. You see, the difference is the storage, the remaining, the remnant. That is it. As is HEC-HMS. So, merci beaucoup for listening, and it is great to have the HEC-HMS. Easy to insert the data and so on. These graphs, and the only difference that I made is this is a daily time step. There it was a monthly. It was a monthly step, January, February. There I converted into daily flow. So it's the same. Sciences, So that's the flow. Merci beaucoup. Thank you for listening.